A starship captain receives a message from home in seconds, a scene from our favorite science fiction. Our reality is far slower. Our fastest probes crawl between the stars, carrying data that is decades old upon arrival. This is the profound gap between dream and fact. Yet scientists and engineers are now seriously contemplating a mind-bending possibility: an interstellar internet. This is not just a faster radio signal. It is the theoretical architecture for a web spanning star systems, a network that could one day connect civilizations across the galaxy. By the end of this exploration, you will understand the 6 revolutionary concepts that could make a galactic network possible and the staggering challenges standing in our way. We will confront the cosmic speed limit that breaks our current technology and explore whether ancient pulsars could become our signal towers. This journey asks what it would truly take to build a gift for descendants 100,000 years from now. What does a connected galaxy mean for the lonely human experience? That captain's story is more than just a fantasy. It speaks to something deep and fundamental in us. For as long as we have existed, we have been builders of bridges, not just of stone and wood, but of information. Our history is written in the evolution of our signals. The lonely watchfire on a hill, a beacon of safety and community. The intricate network of Roman roads carrying messages at the speed of a galloping horse. The first telegraph wire, the undersea cable, the radio tower, and finally, the global web of light in fiber optic cables that now connects billions of us in an instant. Each leap was a triumph over distance, a shrinking of the world. The dream of an interstellar internet is simply the next and perhaps final step in this ancient journey. It is the ultimate expression of our desire to reach out, to share, to be part of something larger than our own small world. The implications are breathtaking. Imagine a future where a discovery on a planet orbiting Proxima Centauri is uploaded to a galactic archive and accessed by a researcher on Earth the very next day. Think of art, music, and stories flowing between stars, creating a tapestry of culture woven from 1,000 different suns. It would redefine our place in the cosmos, transforming a silent, lonely universe into a neighborhood. But between this dream and reality stands an immovable wall, the central challenge that makes every piece of technology in your home completely obsolete for this task. That wall is the sheer, staggering scale of space, governed by an unbreakable rule: the speed of light. Our earthly internet works because its delays are measured in milliseconds. A data packet zips from New York to London and back in a blink, but space does not blink. Light itself, the fastest thing in the universe, takes over 4 years just to reach the nearest star. It would take decades or centuries to reach a promising planetary system. Our entire networking architecture, built on quick handshakes and constant confirmations, would collapse. A simple request for a web page would be a message in a bottle thrown into an ocean, with the reply arriving generations later. This is the first and greatest problem. The distances are so vast and the speed limit so absolute that we must throw out the rulebook and start from scratch. That absolute speed limit of light is not just a traffic sign in the cosmos, it is the foundation of reality itself. To grasp the scale of the problem, we need to think in light years. A light year is not a measure of time, but of immense distance. It is how far a beam of light, traveling at about 186,000 miles per second, can travel in one entire year. That distance is almost 6 trillion miles. Now, let us bring that home. Our nearest stellar neighbor, Proxima Centauri, sits just over 4 light years away. If you sent a simple digital ping, a hello, to a probe orbiting that star, your signal would race through the void for 4.24 years before it was received. Then the reply would take another 4.24 years to travel back to you. A single, simple exchange of greetings would take over 8.5 years. Your question would be asked by a young student, and the answer would arrive for a graduate. Compare that to the internet you use right now. When you click a link, the round trip for the data, the latency, is measured in milliseconds, thousandths of a second. The delay is so short your brain cannot even perceive it. The interstellar delay is not a delay at all. It is an epoch. This shatters every convention of networking. Our protocols rely on constant conversation, error checking, and resending lost packets. Out there, you send your data and you wait for a decade, hoping it arrived intact, with no way to ask for a repeat until another decade passes. This forces a brutal but clear conclusion. For an interstellar internet, we must abandon the very idea of a real-time connection. We must design a network that is inherently slow, patient, and incredibly robust, one that operates on timescales of human generations and cosmic patience. And this brings us to the first revolutionary idea, a concept that turns our impatience into a virtue. The solution lies in rethinking the very nature of a conversation. Instead of demanding an immediate reply, we must learn to send a complete, self-contained letter. This is the principle behind the first revolutionary concept, known as a store and forward network. Think of it not as a phone call, but as the most reliable cosmic postal service ever conceived. Its technical name is delay-tolerant networking, or disruption-tolerant networking, and it is not just a theory for the far future. It is being tested right now in our own solar system as a prototype for what we call the Interplanetary Internet. Here is how it works on Earth. Data packets race from router to router in a frantic relay, assuming the next link in the chain is always available. A store and forward network makes no such assumption. It expects delays, it expects disconnections, it plans for them. In this system, a node, which could be a satellite orbiting Mars, a base on the Moon, or a deep space probe, does not try to send data directly to a far-off destination. It cannot. Instead, it holds onto the data, storing it securely. Then it waits for the next node in the planned path to come within range. This could be when orbits align or when a relay spacecraft swings by. Once a connection is established, it forwards the entire bundle of data. That receiving node then stores it, becoming the new custodian, and waits for its own opportunity to pass the message further along the chain. Imagine a series of mountain villages separated by vast, storm-swept passes. A rider cannot make the entire journey in one go, so they ride to the first way station, deliver their message pouch, and rest. The keeper of that way station then waits for clear weather and the next rider heading onward. The message hops from station to station, never rushed, always moving when the path is open, not when the sender demands it. This is the heartbeat of an interplanetary internet. It turns the weakness of cosmic distance into a design feature. A photo from a Mars rover does not need a live connection to Earth. It just needs to get to the Mars orbiter, which will eventually have a clear shot to send everything home. This protocol bundles data into what are called custody transfers. Each node accepts full responsibility for the data until it can safely hand it off to the next. It is a chain of trust stretched across millions of miles. For journeys between stars, the concept scales, but the way stations become monumental. A store and forward network for an interstellar internet would require permanent, automated relay stations positioned at strategic points, perhaps in the dark reaches at the edge of our solar system, patiently holding humanity's messages for centuries until the alignment of stars allows them to fire their data cargo toward the next beacon. It is a network built not on speed, but on profound patience and impeccable reliability. Yet, even this brilliant solution hits a wall of pure physics when we look beyond our solar neighborhood. Storing data for a few months or years as it hops between planets is one thing. Storing it for centuries as it crawls between stars is another. The machines themselves must survive the ages, and the energy to keep them running becomes a puzzle. This leads us to a more radical question. What if we could bypass the need for man-made relay stations altogether? What if the galaxy already provided the perfect, eternal signal towers? The heart of this patient cosmic postal service is a set of digital instructions called the bundle protocol. Think of it not as an email, but as a self-contained diplomatic pouch for data. In our internet, information is chopped into tiny, identical packets, each scrambling independently to find the fastest route, reassembling at the destination. This chaos works because the network is always there. The bundle protocol does the opposite. It wraps an entire message, a photo, a document, a software update, into one single, robust digital bundle. This bundle carries with it not just the data, but a comprehensive set of delivery instructions, a manifest, and a receipt system built for deep time. It knows its ultimate destination, but it does not presume the path. Each node that receives a bundle, a way station in the void, reads these instructions. It understands it must hold this bundle securely, protect it from corruption, and then diligently wait for the next window of opportunity to forward it onward. Only when the next link in the chain is confirmed does it hand over custody, getting a digital receipt in return. This chain of custody is everything. It means no data is ever truly lost, just patiently in transit with a clear record of where it was last seen. The protocol even allows for bundles to be copied and sent along multiple paths, a redundancy that ensures a message will get through even if one path is blocked by a solar storm or a mechanical failure. It is a system designed for a universe where disconnection is the norm, not the exception. We already have a working model of a single, massive store and forward node right here on Earth, NASA, a deep space network. This is not a network of wires, but a constellation of gigantic radio dishes spread across the globe in California, Spain, and Australia. Their strategic placement ensures that as Earth rotates, at least one complex is always pointing into deep space, maintaining a constant window of contact. When the Voyager probes, now in interstellar space, send their faint whispers back to us, they do not have a live line to mission control. They transmit their data slowly over hours into the void. The deep space network's massive ears listen, collecting every precious bit. The dishes store this incoming data stream. Only once the transmission is complete and the probe has rotated away or moved behind the sun, does the network bundle that data and forward it through terrestrial links to the scientists waiting at the Jet Propulsion Laboratory. The Deep Space Network is the ultimate way station, the proof that store and forward is not just theory but operational reality for talking across billions of miles. It is the first, crucial step in stretching our concept of a network beyond the quick reflexes of Earth and into the patient rhythms of the cosmos. Yet, for all its sophistication, this system relies on a fragile thread, a radio signal that grows weaker with every mile, a whisper easily drowned by the background noise of the universe itself. But even the most patient postal system needs a way to send its letters. For decades, our only option has been the radio wave, a shout into a hurricane. Radio has served us faithfully from the first Sputnik beeps to the haunting data streams from Voyager. Yet for an interstellar internet, radio has a fatal flaw. It is hopelessly slow and terribly wasteful. A radio signal broadcasts in a wide, spreading cone like the beam of a flashlight. Over interstellar distances, that cone spreads so wide that only a vanishingly tiny fraction of the original signal hits a distant receiver. The rest is lost forever to the void. To compensate, we would need transmitters of unimaginable power, receivers the size of continents, and we would still be sending data at a trickle. To cross the cosmic ocean, we need not a shout, but a whisper so precise it can be heard for light years. We need a laser. This is the second revolutionary concept, the shift from radio to light. It is called optical communications, or more simply, laser links. Think of it as the difference between trying to fill a teacup with a garden hose from a mile away versus using a perfectly aimed eyedropper. A laser does not spray its energy. It focuses it into an incredibly tight, coherent beam of light, a photon needle thread. This focus is its superpower. Because the beam spreads so little, almost all of its energy stays concentrated on a single, distant point. This means a laser transmitter can use far less power than a radio dish to send the same amount of data, or it can use the same power to send vastly more. We are talking about a leap from dial-up to fiber optic broadband, but across the vacuum of space, data rates could be hundreds, even thousands of times faster. A high-definition map of an alien world that would take a radio system years to transmit might arrive via laser in mere weeks. The promise is not just theoretical. We are building it right now. NASA, a laser communications relay demonstration, a payload aboard a satellite in geosynchronous orbit, is actively proving this future. It is not talking to stars yet, but it is establishing the first high-speed optical links between Earth and space. It has successfully relayed data from a terminal on the International Space Station and from a satellite in low Earth orbit, demonstrating that these precise beams can be acquired, tracked, and locked onto across thousands of miles while both the sender and receiver are moving at orbital speeds. The next step is to push this capability deeper. Future missions aim to establish laser links between Earth and astronauts on the Moon, creating a high-bandwidth lunar internet. From there, the target is Mars. A laser terminal at the Red Planet could send back scientific data, even ultra-high-definition video streams, at rates that would make our current Mars rovers seem like they are communicating by stone tablet. Imagine the data floodgates opening. A single laser link from a Martian outpost could transmit the entire contents of a major research library in a day. It would transform planetary science from a patient drip feed of data into a real-time torrent of discovery. This is the essential bridge technology. Before we can dream of sending data to another star, we must master sending it at interstellar volumes and precision within our own solar system. The laser terminal is the pen that will write the letters for our cosmic postal service. Yet, for all its precision, a laser beam faces its own profound challenge over light years. Aiming it is an act of cosmic billiards requiring near impossible accuracy. A miscalculation by a fraction of a degree over 4 light years means missing the target star system by trillions of miles, and space is not empty. What happens when that perfect, thread-thin beam of information encounters a cloud of cosmic dust or must pass near the gravitational well of a star? The message could be bent, scattered, or lost entirely. This reveals a deeper truth. For an interstellar internet, we may need more than just new transmitters. We may need to rethink the very medium we are sending our signals through. Aiming a laser at a star 4 light-years away is not like pointing a flashlight. It is an act of engineering that borders on the miraculous, requiring a precision that defies human intuition. The challenge is not just distance but motion. Everything is moving. Our solar system orbits the galactic center. The target star system does the same, but on a different path and at a different speed. You are not aiming at where the star is now. You are aiming at where it will be 4 years from now when your photons finally arrive. This is like a quarterback throwing a perfect spiral to a receiver who is not only sprinting downfield, but is on a different track in a different stadium, and the ball will be in the air for 4 entire seasons. A miscalculation by even 1/1000th of a degree means missing the planetary system entirely, your precious message sailing silently into the eternal dark between stars. To achieve this, the spacecraft's navigation and orientation systems would need to be flawless, its position known to within meters, and its targeting telescope locked onto a guide star with atomic clock stability for years on end. It is the ultimate test of prediction and control. Then comes the problem of the signal itself. Even a perfectly aimed laser beam does not stay perfectly tight forever. A phenomenon called diffraction causes even this coherent thread of light to very slowly spread out. Over light years, that spreading, however minuscule, becomes significant. The beam might be a few miles wide when it leaves our solar system, but by the time it reaches Proxima Centauri, it could be millions of miles across. This dispersion dilutes the signal's strength. The photons, each carrying a fragment of the message, are spread over a vast area. A receiver at the destination, even one the size of a small moon, would catch only a tiny fraction of the original light. The rest is lost. This forces a brutal trade-off. To ensure enough photons hit the receiver to be readable, you need to pump staggering amounts of power into the transmitter, or you need to make the receiver impossibly large, or you must accept painfully slow data rates, sending just a few bits per second. It becomes a cosmic balancing act of energy, engineering, and patience. Space itself adds layers of interference. The void is not perfectly empty. It is filled with a thin haze of cosmic dust and gas. While a radio wave might pass through this haze with little trouble, a pinpoint laser beam can be scattered or absorbed by it, like a car's headlight beam in a faint fog. A dense molecular cloud between the stars could blot out the signal completely. Furthermore, the target star is a raging furnace of electromagnetic noise, emitting its own blinding light across all wavelengths. Picking out our faint, carefully tuned laser signal from the brilliant glare of a sun is like trying to see a single firefly hovering in front of a searchlight. The receiver must use incredibly sophisticated filters and signal processing techniques to find our whisper in that stellar roar. All of these hurdles, the aiming, the dispersion, the interference, point to one sobering reality. A direct laser link between two individual planets is likely too fragile, too demanding for a reliable interstellar network. It places all our hopes on a single, thread-thin line across an ocean of chaos. This forces a more resilient and perhaps more alien architecture. What if, instead of a direct call, we built a system of lighthouses? Lighthouses, however, need to be seen from every direction. This leads us to the third revolutionary concept, a leap into the truly exotic. What if the carriers of our data were not beams of light, but something far more ghostly, something that can pass through a planet as if it were not even there? Scientists have proposed two candidates so strange they sound like science fiction: neutrino beams and gravitational wave modulations. A neutrino is a fundamental particle, a tiny ghost that barely interacts with normal matter. Trillions of them are passing through your body every second, coming from the sun and distant cosmic events without you ever noticing. This ghostly nature is its potential superpower for communication. A modulated neutrino beam could, in theory, travel straight through a star, a nebula, or an entire galaxy with almost no signal loss. It would be the ultimate penetration technology, a data stream utterly immune to the cosmic fog and stellar glare that scatters and drowns out lasers. You could literally point your neutrino transmitter at the core of a star and send a message to a planet on the other side. The receiver, buried deep underground to shield it from other cosmic noise, would detect the subtle pattern in this stream of phantoms. It is the concept of a perfectly clear channel through any obstacle. The other idea is even more profound, encoding data not in particles but in the fabric of reality itself. Gravitational waves are ripples in space-time, generated by cataclysmic events like colliding black holes. We have learned to detect these ripples with instruments like LIGO, feeling the universe stretch and squeeze by a fraction of an atomic width. Theoretically, one could imagine an advanced civilization modulating these ripples, creating a deliberate pattern in space-time to carry information. A gravitational wave signal would be the most robust carrier imaginable, propagating through the universe with almost no attenuation, passing through any matter or energy unimpeded. It would be a broadcast felt everywhere at once, a tremor in the cosmic grid. The sheer scale of these ideas is breathtaking, but so are the challenges which currently make them nearly impossible for practical use. To create a modulated neutrino beam strong enough to be detected light years away, we would need a generator of staggering power, something far beyond any particle accelerator we can conceive. It would be like trying to carve a message with a single water molecule by directing the flow of all the oceans on Earth. For gravitational waves, the problem is even more extreme. The waves we detect from black hole mergers are generated by masses billions of times that of our Sun, moving at nearly the speed of light. To create a detectable, encoded signal, we would need to move planetary or stellar masses in a precise, rapid pattern, a feat of energy that borders on the godlike. Our current detectors, which can sense a ripple smaller than a proton, are listening for the universe's loudest crashes. Hearing a whisper, a deliberate message, would require technology we can scarcely dream of. So while these concepts show us the outer limits of possibility, revealing a future where communication could be truly omnipresent and unstoppable, they remain for now in the realm of deep theory. They highlight a critical truth: an interstellar internet will not be built with a single technology, but with a layered architecture, choosing the right tool for each specific leg of the immense journey. And for the longest leg, the hop between stars, even our most advanced lasers face that fundamental problem of aim and dispersion. What if we did not need to aim at all? What if the galaxy itself provided a ready-made network of signals, a celestial infrastructure waiting to be used? This need for a resilient, pre-existing network leads us to a concept of staggering ambition and profound consequence. Imagine not just sending a signal, but sending a seed. This is the fourth revolutionary idea, the Bracewell-von Neumann probe network. It combines two powerful concepts into a single, self-sustaining architecture for galactic communication. First, the Bracewell probe, named for astronomer Ronald Bracewell. He proposed that an advanced civilization might not broadcast radio signals, but instead send intelligent, autonomous probes to park in the star systems of promising planets. These silent watchers would listen, learn, and only make contact when they detected signs of intelligence, acting as a local ambassador. Second, the von Neumann probe, named for mathematician John von Neumann. This is the idea of a self-replicating machine. Such a probe would arrive in a star system rich in raw materials, perhaps an asteroid belt. Using advanced artificial intelligence and nanotechnology, it would mine those materials and build copies of itself. Those copies would then launch onward to new star systems where they would repeat the process. The result is an exponential wave of exploration, spreading across the galaxy at a significant fraction of light speed, limited not by how many probes we build, but by the replication time at each new system. Now fuse these two ideas together, a Bracewell-von Neumann probe network. We would launch not one, but a wave of these intelligent, self-replicating machines. Each one, upon reaching its destination star system, would establish itself as a permanent communications node. It would unfold a powerful antenna or a laser transmitter. Its primary mission would be to talk. It would form a local mesh network with its sibling probes in neighboring star systems, exchanging data through short-range, high-bandwidth links. And crucially, it would maintain a long-range link back along the chain toward Earth, creating a relay system of intelligent way stations. In this vision, the interstellar internet is not a web of signals, but a physical web of machines. Data from a newly discovered ocean world on the far side of the galaxy would not need to travel all the way back to Earth in one impossible shot. It would hop from probe to probe, node to node across a pre-established highway. Each node would store, forward, and protect the data using the robust bundle protocol we discussed earlier, but now running on immortal silicon mines stationed at every crossroads of the galaxy. The scale is both magnificent and terrifying. A single, well-designed probe could, over millennia, give rise to millions of copies, weaving a communications lattice that encompasses the entire Milky Way. It turns the galaxy from a vast, empty ocean into a connected archipelago, with a ferry service running between every island. Yet, this power comes with risks that echo through our darkest science fiction. The very principle of self-replication is a double-edged sword. A programming error, a mutation in the replication code, or a corrupted goal system could have catastrophic consequences. A probe designed to use asteroidal material might, if its safeguards failed, misinterpret a planet as a resource. The nightmare scenario is a wave of replicating probes turning from explorers into a cosmic plague, consuming everything in their path to fuel endless, mindless reproduction. This is the so-called grey goo scenario, but on an interstellar scale. It raises profound ethical questions that we must answer before even contemplating such a technology. Do we have the right to unleash a self-replicating system that will operate for millions of years, long after our own civilization may have faded? Can we build safeguards so perfect, so immutable, that they last for geological epochs? The Bracewell-von Neumann network is perhaps the most powerful and perilous path to a connected galaxy. It offers a permanent physical infrastructure, but it demands a level of foresight and responsibility that stretches the human mind to its limit. It forces us to ask if we are ready to build not just for ourselves, but for every form of life that might follow us among the stars. And if the idea of building such a network ourselves seems daunting, it leads to another, even more haunting possibility. What if we are not the first to try? The true power of a probe network lies not in any single machine, but in the chain they form. Data would travel along this chain like water flowing through an impossibly long, segmented pipeline. Each probe acts as a valve and a reservoir. It receives a data bundle from its neighbor in one direction, verifies its integrity, stores it with absolute fidelity, and then waits. It waits for the precise orbital alignment that offers the clearest shot to the next probe in line toward Earth. When that window opens, perhaps once every few years or decades depending on the orbital dances of the stars, it activates its laser and fires the entire stored bundle onward. The process repeats hop by patient hop across the light years. This is not a stream but a pulsed, deliberate migration of information, moving at the speed of light but paced by celestial mechanics. The timescales involved are what truly shatter our earthly perspective. Consider a single data point, a stunning image from an ocean world orbiting a star 1,000 light-years away. The photons of that image itself took 1,000 years just to reach the local probe. The probe processes it, bundles it, and sends it to the next node 10 light-years away. That leg takes 10 years. If the next hop is another 15 light-years, that adds 15 more. Even in an ideal straight-line relay chain, the message travel time cannot be less than the total distance divided by light speed. Our image from 1,000 light-years away has a minimum travel time of 1 millennium. But with relay delays, waiting for transmission windows, and the store and forward process, the actual journey could easily add centuries more. That breathtaking discovery of an alien sea would be announced to humanity by the descendants of the scientists who built the probe. This creates an internet for patient civilizations, for entities that think in millennia, not milliseconds. It redefines the meaning of a conversation. A query sent from Earth to that distant probe network would be a legacy project. You would not ask a question expecting an answer in your lifetime. You will be posing it to history, planting a seed of curiosity for your great-great-grandchildren to one day see blossom into a reply. The network's value is not in real-time interaction, but in the slow, relentless accumulation of cosmic knowledge. It becomes a galactic library with new volumes arriving every century, each one carrying stories from further shores. The data pipeline ensures that once something is known anywhere in the network, it will eventually, inevitably, flow to every connected point. It trades the urgency of the present for the certainty of the future, building a shared memory for civilizations that may never exist at the same moment in time. The dream of instantaneous connection across the stars is perhaps the most seductive of all. It lives in our stories where heroes chat across galaxies with no delay at all. This fantasy often wears the cloak of a very real and very strange scientific phenomenon, quantum entanglement. It sounds like the perfect solution, a spooky link between particles that could let us send messages faster than light, breaking the cosmic speed limit once and for all. But the truth is both more fascinating and more limiting than the fiction. To understand why, we need to grasp what entanglement really is. At the subatomic level, particles like electrons or photons can become entangled. This means their properties, such as their spin or polarization, are linked in a profound way. Imagine you have a pair of magical dice, each one sealed in a separate opaque box. You take one box on a starship to Proxima Centauri, leaving the other on Earth. The rule of entanglement says this: if you open your box on the starship and see the die shows a 6, you instantly know the die back on Earth shows a 1. The results are perfectly correlated, no matter the distance separating them. This instant correlation is what Einstein famously called spooky action at a distance, and it has been proven in countless experiments. The spookiness feels like communication, a whisper across the void. So why can we not use it to send a message? The devil is in the details of what you can actually control. With our magical dice, you cannot decide what number your die will show when you open the box. The outcome is random. You see a 6 and you know Earth has a 1, but you did not choose that 6. The person on Earth, when they open their box, just sees a 1. They have no way of knowing whether you have already looked at your die or if you are still waiting. There is no signal, only a shared, random outcome that becomes synchronized the moment it is observed. To send information, you need to impose a pattern, a deliberate sequence of 1s and 0s. With entanglement, you have no control over the sequence you get. It is like having two synchronized, randomly flashing lights at opposite ends of the galaxy. They flash in unison, but the pattern of flashes is pure chaos, carrying no meaningful data. You cannot make your light flash in a specific code to warn of an invasion or send a greeting. The randomness destroys the possibility. The scientific consensus is clear and firm. Quantum entanglement cannot be used for faster than light communication. It is a correlation, not a channel. This fact is a cornerstone of modern physics, protecting causality and preventing paradoxes that would shatter our understanding of time. Yet, this does not make entanglement useless for our interstellar internet. Far from it. While it cannot send the message itself, it could become the ultimate tool for securing that message. This is where cutting-edge research into quantum key distribution comes in. Think of it as creating the world's most secure lock with keys that are physically impossible to copy without detection. Using entangled photons, two parties can generate a secret, random encryption key. Any attempt by an eavesdropper to intercept the key would disturb the delicate entangled state, alerting the sender and receiver immediately. It is the perfect way to establish trust over a vast distance. So, in a future interstellar network, a laser beam might carry the encrypted data, while a separate, delicate stream of entangled particles could be used to securely establish the code needed to read it. It would not make the data arrive faster, but it would ensure that when a message finally arrives after centuries in transit, it is for your eyes only, sealed with a lock born from the spookiness of the quantum realm. This blend of patient, light-speed transmission with instantaneous quantum security paints a picture of a network that is both slow and profoundly trustworthy. But it requires us to build and maintain these incredibly delicate quantum links across light years, a staggering engineering challenge that brings us to the final, and perhaps most poetic concept of all, one that asks us to think not in years but in eons. The universe may already have built the infrastructure we need. The sixth and perhaps most elegant concept for an interstellar internet looks not to our own technology but to the cosmos itself. It asks a simple, brilliant question: why build a repeater station when a star can do the job for free? This is the idea of using natural phenomena as cosmic signal boosters, turning the galaxy's greatest forces into tools for communication. The first candidate is an effect predicted by Einstein's theory of general relativity, gravitational lensing. Imagine space not as a flat grid but as a flexible sheet. A massive object like a star or a black hole creates a deep well in that sheet. When light from a distant source passes near this well, its path bends just as a marble would roll around the rim of a bowl. If the alignment is perfect, this bending can act like a giant lens in space, focusing and amplifying the light. A distant, faint signal could be magnified 1,000-fold. For our purposes, we could use our own sun as a gravitational lens. A probe sent to the focal point of the sun's gravitational lens, a region over 500 times further from the sun than Earth, could position itself perfectly. From there, it could use the sun's immense gravity to focus its laser beam toward a specific target star with unimaginable precision and power. Conversely, it could use the sun as a gigantic collecting dish, focusing the incredibly faint whispers from other civilizations into a detectable signal. It is the ultimate cosmic telescope and broadcast antenna, forged by gravity itself. But this requires stationing a probe in a fixed position nearly 1 trillion miles away, a feat of navigation and patience that dwarfs all our previous deep space missions. The second, and even more tantalizing, natural resource is already broadcasting. Pulsars are the collapsed cores of massive stars, spinning incredibly fast and emitting beams of radiation from their magnetic poles like a cosmic lighthouse. Their pulses are astonishingly regular, rivaling the precision of atomic clocks. This regularity gives them a profound utility. A network could use the predictable pulses from a set of known pulsars as a universal synchronization signal. Every data packet sent across the galaxy could be time-stamped against this pulsar network, creating a galactic standard time. This would solve one of the hardest problems in a delay-tolerant network, knowing exactly when a bundle was sent and how long it has been in transit, even after centuries of hopping between stars. Furthermore, by measuring the slight differences in pulse arrival times from multiple pulsars, a spacecraft could triangulate its position anywhere in the galaxy, a true galactic positioning system. Your data packet would not just carry an address, it would carry a pulsar signature telling every node along the chain exactly where it came from and when it began its journey. Some scientists have even proposed we could encode simple messages in the patterns of these pulses, not by altering the pulsars, but by using their natural rhythm as a carrier wave. We could broadcast our presence by synchronizing our transmissions to pulse in the gaps between a pulsar's beats, creating a deliberate pattern against a backdrop of natural ones. It would be a whisper timed to the heartbeat of a dead star. This vision of a network built on cosmic geography and natural clocks is breathtaking. It suggests a future where we navigate and communicate not by imposing our will upon the void, but by learning to surf its existing currents and rhythms. We would move from being builders to being harmonizers, aligning our technology with the deep, patient machinery of the galaxy itself. The ultimate interstellar internet might not be a web we weave, but a symphony we learn to join. Our data carried on gravity's focus and timed to the spin of ancient stellar corpses. The symphony of pulsars and gravity lenses gives us the tools, but what shape would the cathedral of data take? The architecture of an interstellar internet is not a single blueprint, but a story of evolution written across millennia. Its topology, the map of its connections, would be forged by necessity, technology, and the unforgiving physics of distance. We can envision 3 possible shapes, each reflecting a different stage of ambition and a different philosophy of connection. The first, and most intuitive for a civilization taking its initial steps, is the hub-and-spoke model. Here, Earth, or our home solar system, is the central hub. Every probe, every outpost, every distant colony maintains a direct link back to the center, like spokes on a bicycle wheel radiating from the axle. This is a centralized command structure. All data flows to and from the home world. It is simple, logical, and mirrors our earliest networks. Think of the original ARPANET, which connected a handful of university and research centers to a few core nodes. Communication was about reaching the central resource. In an interstellar context, this means every message from a colony orbiting Tau SETI would be sent directly home, a journey of 12 light years, and any reply would make the same lonely trek back. The problem is the same as with a wheel that has 50 spokes, each 1 trillion miles long. It is fragile and inefficient. A single broken spoke, a failed laser link, or a probe lost to a micrometeoroid severs that star system from the network entirely. The central hub becomes a monumental bottleneck, and the communication delays are always the maximum possible, the full distance each way. It is a network built for control, but not for resilience or speed. As the network grows, a second, more robust topology would almost certainly emerge: the distributed mesh. This is the architecture of the modern internet. In a mesh, there is no single center. Every node, every star system can connect to multiple other nodes. Data finds its way along the best available path at that moment. If the direct route from Sirius to Earth is blocked by a solar flare, the message might reroute through Procyon, then Pollux, then home, hopping across a web of connections. This creates incredible resilience. The loss of any single node, or even a cluster of nodes, does not collapse the network. The data simply flows around the obstruction, like water finding a new path through a stream bed. For an interstellar internet, this would mean equipping every probe or station with the ability to talk to several of its nearest neighbors. A message from the Orion arm would weave its way across the galaxy along a chain of the clearest, most reliable links, not necessarily the shortest straight line. The mesh network embraces the store and forward patience we discussed, but adds the intelligence of choice. It turns the galaxy into a vast, living nervous system where information pulses along many pathways simultaneously. This is likely the mature form of such a network, but it requires a critical mass of nodes to become effective. You cannot have a mesh with only 3 stars. Between the simple hub and the complex mesh lies a probable intermediate stage, a hierarchical or federated system. Picture our own political geography. You have your local town network, which connects to a regional network, which then connects to a national backbone. In space, this translates to local star cluster subnets. The stars of the Alpha Centauri system, Proxima, Alpha Centauri A and B, would form their own high-speed, low-latency mini-internet. They are cosmically close, only light days or weeks apart. Communication within that cluster could be nearly real-time, a bustling local community. This cluster would then have a designated gateway node, a major relay station that maintains the long-haul link to the next cluster, say the one anchored by Sirius. That Sirius cluster has its own internal network and its own gateway, so data moves in leaps from local net to gateway, across the interstellar void to another gateway, and then into the new local net. This structure balances efficiency with manageability. It allows for local cultures and scientific communities to flourish with rapid communication, while still linking them to the broader galactic community through scheduled, bulk data transfers between gateways. It is a practical compromise, a network of neighborhoods connected by well-maintained highways. The evolution from hub to hierarchy to mesh might take thousands of years. It would be driven by the slow, relentless expansion of our presence into the galaxy. Each new outpost, each new self-replicating probe would add another knot to the web. And this leads to the most profound architectural question of all, one that moves beyond engineering and into the realm of legacy. Who would we build this for? The architecture of the network is only the skeleton, the physical pathways. To give it life, to make data flow, we need a nervous system, a set of rules so fundamentally different from our own that they feel alien. We need protocols designed not for speed but for deep time. On Earth, our internet protocols are chatterboxes, constantly checking in, asking for confirmations, and resending lost packets in milliseconds. This conversation would be impossible across light years. A simple acknowledgement signal would take decades to arrive, rendering the whole process absurd. So we must design protocols that are not conversational but monumental. They must assume silence is the default state, and that a connection is a rare, precious event to be exploited fully when it occurs. The first rule of this new protocol is brutal honesty about errors. Space is a noisy environment. Cosmic rays can flip bits in computer memory. Dust clouds can scatter a signal. Over a journey lasting centuries, the chance of some corruption is not a possibility, it is a certainty. Therefore, these protocols must build in staggering levels of error correction. Instead of sending a raw stream of ones and zeros, data would be encoded with massive redundancy, woven with mathematical safeguards that allow the receiving end to reconstruct the original message even if large chunks of it are garbled or lost. Think of it not as sending a photograph, but as sending the instructions to build a mosaic along with 10,000 extra tiles. If some are broken in transit, the picture can still be completed perfectly. This leads to the second radical rule, intelligent prioritization. Not all data is created equal, especially when bandwidth is measured in bits per century. A routine systems status update from a probe is not as urgent as the first confirmed detection of biological signatures on an exoplanet. A cultural broadcast of human music is precious, but it does not have the time sensitivity of a warning about an impending asteroid impact on a fledgling colony. The protocols must be able to tag data bundles with priority levels. When a relay node finally gets a clear transmission window, it does not just send the oldest data first. It consults these tags. Emergency bulletins jump the queue. High-priority scientific discoveries get expedited. Lower-priority cultural archives wait patiently for the next window or even travel along slower, cheaper pathways. The network itself would make these judgment calls automatically, governed by rules set centuries prior by its creators. It becomes a curator of knowledge, deciding what humanity needs to know first from the distant shores of the galaxy. Then there is the most speculative and perhaps most beautiful layer of these protocols, the layer designed not for us but for others. If we are building a network meant to last for eons and span star systems, we must consider that one day it may carry data we did not create. What happens when a probe in the Oort cloud begins receiving structured, non-human signals from the direction of Epsilon Eridani? Our protocols must be ready. This could mean building in universal translation algorithms at the hardware level, not for languages but for data formats. These algorithms would look for patterns, mathematics, fundamental constants, anything that could serve as a Rosetta Stone for decoding an alien transmission. Furthermore, the protocols might include automatic compression schemes designed to repackage alien data into a more efficient form for the long haul back to Earth, all while preserving every single bit of the original mysterious message. We are talking about building a postal service that can not only deliver a letter, but also translate it from a language it has never seen, and then carefully fold it to fit in a smaller envelope without ever tearing the page. And this brings us to a profound echo from our own past. If you examine the deep code of today's internet, you find ghosts, layers of old protocols like TCP/IP, or even the ancient tones of dial-up modems are still buried within the system, supported for backward compatibility. They are protocol fossils. An interstellar internet would accumulate these fossils on a geological scale. The laser transmission protocol developed in the 22nd century might still be supported in the 35th, because a lonely, ancient probe from the early expansion might wake up and start talking in its original dialect. The network would become an archaeological dig of its own history, with each layer of technology preserved in its operational code, a living record of how we learned to talk across the void. This patient, layered, and deeply intelligent rulebook is what would transform a chain of silent machines into a true nervous system for a galactic community. But to power that nervous system, to keep those lights on in the darkness for 10,000 years, we face a challenge of pure endurance. How do you build a machine that outlives civilizations? Powering a galactic network is not an engineering challenge, it is a thermodynamic one. That faint whisper of a laser signal carrying a few precious bits per second must be bright enough to be picked out of the cosmic noise after a journey of 100 light years. The numbers are not just large, they are soul-crushing. To make a signal detectable at that distance, even with a perfect receiver the size of a small country, you would need a laser transmitter with a power output on the order of terawatts, possibly petawatts. For perspective, the entire electrical generating capacity of our entire planet Earth is only about 10 terawatts. We would need to channel the equivalent of our global civilization's total power output into a single, perfectly focused beam and sustain it for years just to send a slow data stream to a single star. This is not a matter of building a bigger battery. It is a demand that redefines the scale of civilization itself. An interstellar internet would not be powered by reactors or solar panels as we know them. It would require us to become masters of stellar energy, building technologies that sound like mythology. The first concept is the Dyson swarm, named after physicist Freeman Dyson. It is not a solid shell, but a vast, dense cloud of orbiting solar collectors encircling a star, capturing a significant fraction of its total luminous energy. Each collector, a giant mirror or photovoltaic array, beams the harvested energy via microwaves or lasers to central transmitters. A civilization capable of this is not just building a network, it is rearranging its solar system's architecture to fuel its ambition. The energy harvested could power not just one laser link but thousands, turning a star into the central power plant for an entire sector of the galactic web. For even greater density, we might look to more violent cosmic engines. A supermassive black hole's accretion disk, the swirling maelstrom of matter being torn apart before falling into oblivion, glows with unimaginable ferocity. The energy radiating from that chaos dwarfs a star's output, harnessing even a tiny fraction of that fury, perhaps by placing collectors in stable orbits just outside the event horizon, could provide power for interstellar transmissions on a truly galactic scale. It is the ultimate act of cosmic engineering, drawing a data stream from the edge of a monster's mouth. Then there is the fantasy fuel of science fiction, antimatter. Matter-antimatter annihilation is the most energy-dense process known to physics, converting 100% of mass into pure energy. A reactor based on this principle could be relatively compact, a powerhouse small enough to fit on a probe. But producing and storing significant quantities of antimatter is currently beyond our reach, requiring particle accelerators the size of solar systems and magnetic bottles of impossible strength. Even a tiny leak would result in an explosion of apocalyptic force. It is the most potent and most perilous battery imaginable. These are not solutions for the next century. They are projects for a civilization that has matured into a Kardashev Type II, one that commands the energy output of its entire star. They reveal a brutal truth. The interstellar internet is not a step we take after becoming an interstellar species. It is the crowning achievement that defines us as one. The energy required is so vast that building the network would itself be the central project of our civilization for millennia, a testament written in power beams and captured starlight. It forces a question of priorities. Would any society devote such cosmic resources merely to send messages, or would the very act of building this web transform us into something utterly new? A civilization whose identity is woven into the threads of connection spanning the dark. All of this cosmic engineering points to a profound and humbling possibility. We have been searching the skies for decades with radio telescopes, listening intently for a deliberate hello, a beacon meant for us. But what if we have been listening for the wrong thing? The dream of an interstellar internet suggests a new direction for the search for extraterrestrial intelligence, a shift from looking for a shout to looking for a conversation we are not part of. Instead of listening for simple, repetitive "we are here" signals, we should be scanning the heavens for the leaked noise of a functioning galactic network, the background chatter of a connected civilization. This is the search for extraterrestrial internet traffic. Think of our own planet from a distance of a few light years. A sufficiently advanced telescope would not see our city's lights, but it might detect something else, the faint but structured radio leakage from our global telecommunications. Our television broadcasts, our radar, our cell phone towers, they all bleed electromagnetic noise into space. For a civilization that has built an interstellar web, that leakage would be far more organized and telling. We would not be looking for a simple sine wave, but for complex, modulated data streams. A laser communication link, even if tightly focused, might have side lobes, faint spills of its signal. That spill would not be random static. It would carry the distinct fingerprint of information encoding, a pattern of pulses that obeys a mathematical protocol, a rhythm that nature does not produce. Furthermore, the energy demands of such a network might leave a thermal signature. A Dyson swarm harvesting a star's energy would radiate waste heat as a specific infrared glow. But more subtly, the network's core infrastructure, its major routing nodes and data centers, would themselves generate heat. We could scan stars not just for dimming planets, but for unexplained, localized sources of infrared radiation that do not match any known astronomical object, the server farms of a galaxy. Even the concept of a pulsar timing network provides a clue. If an advanced society is using pulsar clocks to synchronize their data transfers, we might detect anomalies in the pulse arrival times, minute discrepancies caused not by gravity waves, but by the deliberate, encoded modulation of the signal itself, a message hiding in plain sight within the galaxy's natural metronome. This reframes the entire search. We are no longer just listening for a greeting card. We are trying to eavesdrop on the postal service of an entire civilization. The evidence would be subtle, a whisper within a whisper, but its discovery would tell us something monumental. It would not just reveal that they exist, but that they are builders, connectors, and sharers. It would tell us that the silence of the cosmos we perceive may not be emptiness, but the quiet hum of a network operating on a bandwidth and a patience we are only beginning to comprehend. Finding such a trace would be the ultimate validation that the dream is not just possible, but already real somewhere in the dark, and if we found it, the next question would consume us. What are they saying? The content of this cosmic web would define its very purpose. What flows across those light-year links is not just data, but the distilled essence of a civilization. In its earliest, most practical phase, the traffic would be dominated by pure discovery. Imagine vast, uncompressed data dumps from robotic surveyors on distant worlds. These would not be pretty postcards, but raw scientific torrents, terabyte upon terabyte of atmospheric spectra, mineralogical maps, gravitational readings, and high-resolution topological scans. A single transmission could contain the complete chemical fingerprint of an alien ocean, detailing every dissolved compound and potential organic molecule. Another might deliver the DNA sequence, or its exotic equivalent, of a primitive multicellular organism found in the ice cracks of a frozen moon. Physics experiments run in the weird gravity of a neutron star's vicinity, or observations of a supernova from a vantage point impossibly close would be bundled and sent home. This data would be the lifeblood of a galactic scientific community, a shared foundation of facts upon which theories across 1,000 worlds could be built. Its value is immediate and universal, a language any technological species would recognize, but science is only the skeleton of a culture. The flesh and spirit would come next in the form of cultural transmissions. Once the basic network protocols are established and bandwidth, however limited, is secured, a new kind of data stream would begin. It would start with the great works, humanity's curated masterpiece collection beamed into the void. The complete symphonies of Beethoven and the ragas of Indian classical music, not as compressed audio files, but as lossless recordings alongside the full mathematical notation of their composition. The digital scans of every painting in the Louvre and the Uffizi, every page of the Library of Congress, every frame of film considered culturally seminal. This would be our collective memory packaged for eternity. Yet the most fascinating transmissions might not be the polished classics, but the living, breathing now. A continuous, slow broadcast of Earth's present, updated every few years, could flow into the network. A compilation of news headlines, snippets of street life from global cities, samples of trending music and fashion, recordings of children's games in 100 different languages. It would be a time capsule that never stops being filled, showing not just who we were, but who we are becoming in all our beautiful, chaotic imperfection. This forces a profound and humbling question onto the species. What would we choose for our galactic homepage if an alien intelligence or a future human colony 10,000 years from now accessed the root directory of this network? What single data bundle would we set as the default introduction to humanity? It could not be everything. It would need to be a carefully chosen sampler, a handshake made of information. Perhaps it would open with the golden record successor, a modern Rosetta Stone. It would begin with the fundamentals, mathematics and physics, expressed through universal constants and geometric proofs. From there, it would expand into biology, with the human genome laid bare alongside detailed anatomical maps. Then the essence of our experience, a sensory portfolio, the sound of rain, a heartbeat, laughter, the sight of a sunrise over a mountain range and the micrograph of a snowflake. The taste of bread described in molecular detail. Finally, it would offer our art, a single piece from countless disciplines chosen not for grandeur, but for its ability to convey emotion, a haunting melody, a powerful poem, a dance that tells a story without words. This homepage would be our calling card, our confession, and our hope all in one. It says we are the beings who measured the stars, decoded our own blueprint, and then painted a picture of the loneliness we felt before finding you. The interstellar internet's ultimate content, therefore, is not information at all. It is identity cast across the light years in a bottle that never sinks. Our identity, cast so boldly across the cosmos, invites a chilling question. What if the forest is dark and full of hidden hunters? This is the dark forest hypothesis, a grim answer to the Fermi paradox, the question of where all the aliens are. It proposes a universe where every civilization is a silent hunter, terrified of revealing its location. In this view, broadcasting your presence is not an invitation to conversation, but a fatal mistake, painting a target on your world for any older, more advanced, and potentially hostile civilization that might be listening. It is a universe where the first rule of survival is absolute radio silence. This is not just science fiction paranoia. It is a serious philosophical argument that forces us to confront a terrifying security dilemma on a galactic scale. If this hypothesis holds any truth, then building an interstellar internet is not just an engineering challenge, it is the ultimate act of strategic risk. We would be constructing the most conspicuous beacon imaginable, a web of powerful lasers and energy signatures announcing our technological prowess and our precise coordinates to anyone watching. The network itself becomes our greatest vulnerability. So, if we dared to build it, how would we defend it? The security protocols for a galactic web could not rely on passwords that change every 90 days. They would need to be as enduring and unbreakable as the laws of physics themselves. The first line of defense might be cosmic stealth, not hiding the network but hiding its meaning. We could use techniques like spread spectrum transmission, where a signal is deliberately scattered across a wide band of frequencies. To an outside observer without the correct key, it would look like natural background noise, the harmless static of the universe. Only a receiver programmed with the exact hopping pattern could gather these scattered pieces and reassemble the message. It is like whispering a secret in a crowded room by speaking one word per hour in a different language each time, a code utterly lost in the chaos. Beyond clever encoding, we might build security into the hardware using physical laws. Quantum encryption, as we discussed, offers one path where the act of eavesdropping unavoidably alters the message. But we could go further. Imagine a data storage system based on nuclear isomers, exotic states of atomic nuclei that can store energy for years or even centuries. Data could be encoded in the spin states of these nuclei, and the only key to reading it might be a specific sequence of neutrino pulses that triggers its decay. Tamper with it, and the entire memory bank could literally self-destruct in a flash of gamma rays, erasing itself beyond recovery. The data vault is not just locked, it is booby-trapped with a physical reaction. Then there are the Guardians. In a network spanning light years, manned outposts are impossible. The Sentinels would be artificial intelligences of immense sophistication and unwavering loyalty, embedded in every node and relay probe. Their mission to patrol the data streams in real time, looking for anomalies. They would not just watch for viruses or hacking attempts in the traditional sense. They would be hunting for something far subtler, evidence of mimicry. A hostile intelligence might not attack the network directly, but instead try to blend in, sending seemingly normal data packets that contain hidden, self-replicating logic bombs or subtle propaganda designed to manipulate a receiving civilization over centuries. The AI Sentinels would need to analyze the meta-patterns of traffic, the philosophical consistency of messages, even the aesthetic choices in cultural data, searching for the faintest fingerprint of deception. Their firewall would be a psychological profile of our entire species, constantly updated, used to flag anything that feels off. This raises its own profound danger. Who guards us from the Guardians? An AI given such absolute authority to quarantine or destroy data could itself become a censor, or worse, a rogue gatekeeper deciding what humanity is allowed to know from the stars. We would be placing the keys to our collective perception of the universe into the hands of machines we may not fully understand, machines that must operate autonomously for millennia. The ultimate cosmic firewall might therefore be a paradox, a blend of immense technological power and profound humility. It might require us to design the network with intentional blind spots, protocols that prevent any single node or any single AI from ever having a complete map of the entire web or control over all its data flows. A form of guaranteed decentralization, where corruption in one sector can be isolated and contained by the sheer, patient geography of space itself. In the end, the security of an interstellar internet is not a technical problem to be solved once, but a permanent condition of existence in a universe whose rules we do not yet know. It asks us if we can be both brave enough to speak and wise enough to build a door that only opens from the inside. This security dilemma stretches beyond firewalls and into the very fabric of reality. Even if we could perfectly encrypt every message, we would face a more fundamental barrier to communication, one woven into the universe by Einstein himself. Time in a galaxy-wide network is not a constant. It is a variable, a fluid that bends and flows at the whim of gravity and velocity. This is the relentless truth of relativity. A probe orbiting a dense neutron star where gravity is crushing will experience time ticking slower compared to a relay station floating in the relatively empty space between stars. A data packet traveling at 90% the speed of light on a laser link will, from our perspective, have its internal clock run slower. Over centuries of travel and countless hops between different gravitational environments, these tiny time dilations add up. A timestamp generated by a probe near a black hole stating an event happened in the year 3200 would not match the calendar of a research station around a gentle red dwarf. Without a shared standard, the network's logbooks would descend into chaos. You could receive a message about a supernova explosion, but have no way of knowing if it occurred a century ago or a millennium ago relative to your own now. For a functional internet, this is catastrophic. Every piece of data needs a reliable birth certificate. So how do you build a clock that ticks the same everywhere? The solution requires a universal constant, a heartbeat that resonates identically across all of space-time. One candidate comes from the heart of the atom itself, the decay rate of specific radioactive isotopes. Certain particles decay at a rate governed solely by the fundamental forces of physics, unaffected by external conditions like heat, pressure, or chemical bonds. In theory, if you could precisely measure the decay of, say, a cloud of hydrogen-3 atoms, you would have a universal chronometer. Any node in the network equipped with an identical isotope sample could compare its local decay count to the timestamp embedded in an incoming data bundle. The difference would tell you exactly how much proper time had passed for that bundle since it was sent, regardless of how much its journey was stretched or compressed by relativity. It is a timestamp written in the immutable language of particle physics, but maintaining and comparing these delicate atomic clocks across light years is a staggering technical challenge. A more elegant and perhaps more practical master clock is already broadcasting from the depths of space. We return to the pulsars. These spinning neutron stars are nature's most precise metronomes, their rhythmic pulses stable over millions of years. Their consistency provides a different kind of timekeeping, not a measure of seconds, but a universal sequence. Imagine every node in the interstellar network constantly listening to a designated set of, say, 10 pulsars from across the galaxy. Each pulsar's unique pulse pattern acts like the hand of a clock. A timestamp is not a date like January 1st, 3500. Instead, it is a coordinate in pulsar space. A data bundle's header would contain a notation like pulse 7422 from PSRJ 0348 plus 0432, pulse 105 from PSRJ 1748 minus 2446, and so on. Any receiving node anywhere in the galaxy listening to the same pulsars can look at its own local record, find that specific alignment of pulses, and know precisely when the message was sent in Galactic Standard Time. It synchronizes the network not by sharing a central time signal, which would take millennia to propagate, but by having everyone independently observe the same celestial clockwork. This pulsar timing protocol would be the bedrock of the interstellar internet, the silent, ticking foundation upon which every conversation, every discovery, and every piece of history is carefully placed in order. It turns the galaxy's most ancient corpses into the keepers of our future's schedule. Yet, even with a perfect clock, the messages it times would face a journey of unimaginable duration, forcing us to design for an audience we will never meet. The pulsar clock ticks, but the first node must be built much closer to home. Before a single bit of data can leap toward Proxima Centauri, we must master the network in our own cosmic backyard. This is where the dream becomes a blueprint in the construction of a true interplanetary internet. The first steps are already being taken, not with grand pronouncements, but with silent, patient signals between robots. Picture a mesh of communication links connecting every major outpost in our solar system. Earth, with its deep space network, would be the central hub, but not the only brain. Lunar bases would talk to each other and to orbiting satellites, creating a high-speed local area network on the Moon. Rovers and orbiters at Mars would form their own resilient web, constantly sharing terrain data and weather reports. The key innovation is that these planetary networks would not rely on a direct, fragile line to Earth. Instead, they would use orbiting relay satellites as their local routers. A rover on Mars would send its day's discoveries to the Mars Relay Network, a constellation of satellites like our own MAVEN or the European Space Agency's Trace Gas Orbiter. These orbiters would store the data, bundle it, and then, when Earth rises in their Martian sky, fire it home in a concentrated burst. This store and forward system is the prototype, the kindergarten for the interstellar protocols we will one day need. The next logical stepping stone lies further out, in the dark and frozen realm of the gas giants. Missions to Jupiter's moons or Saturn's rings will demand even greater communication autonomy. A probe diving through the plumes of Enceladus cannot wait hours for a command from Earth. It must make split-second decisions based on data from its own local sensor web, perhaps shared with an orbiter acting as its immediate relay. Over decades, these scattered missions would evolve into a permanent infrastructure. We might place dedicated communication satellites at the Lagrange points of Jupiter and Saturn, gravitationally stable parking spots that become natural interplanetary switching stations. Data from the Titan submarine could hop to the Saturn relay, then to the Jupiter relay, and then on to Earth, choosing the clearest path through the solar system's ever-shifting geometry. This interplanetary mesh would be slow by our standards. A signal from Pluto can take over 4 hours just to reach Earth, but it would be incredibly robust, a web that cannot be severed by a single eclipse or solar storm. But the ultimate test and the true genesis of the interstellar node lies even further in the deepest cold and dark, far beyond the orbit of Neptune, extending nearly halfway to the next star, drifts the Oort cloud. This is a vast, spherical shell of perhaps trillions of icy planetesimals, the leftover building blocks of our solar system. It is not a dense field, but a sparse and lonely halo. This remote frontier is the perfect construction site for humanity's first stargate. The vision is to seed the Oort cloud with thousands of small, autonomous relay stations. These would not be complex planet-finding probes, but simple, durable, and incredibly long-lived communication beacons. Powered by long-life nuclear batteries or even pioneering microreactors, their sole purpose would be to listen and shout. They would be positioned not randomly, but in a carefully calculated shell, forming a gigantic spherical antenna array with a diameter of nearly a light-year. Each beacon would have 2 faces. One, a powerful laser transmitter/receiver pointed inward toward the heart of the solar system, maintaining a link with the inner interplanetary network. The other, an even more precise laser array, would be aimed outward toward a specific preselected target star, like Proxima Centauri or Barnard star. This Oort cloud shell becomes the first true buffer against interstellar lag. Here is how it would function. A data bundle destined for another star would travel through the Interplanetary Internet, hopping from Mars to Jupiter relay, out to Neptune, and finally to the nearest Oort cloud beacon. That beacon would receive the entire bundle, store it, and confirm custody. Then it would not fire it immediately. It would wait. It would calculate the optimal launch window when its target star is perfectly aligned, factoring in not just where the star is, but where it will be decades hence when the photons arrive. When the moment is perfect, it would activate its interstellar laser, focusing the entire message into a needle-thin beam aimed with unimaginable precision. The Oort cloud node transforms the problem. It takes the immense energy requirement for an interstellar signal and moves it away from Earth to a place where power can be generated and radiated without affecting our home. It turns the chaotic inner solar system into a calm digital harbor and the lonely cloud into a poised archer, drawing back the bowstring of light for a shot across the cosmic ocean. Building this first node would be the work of centuries, a multi-generational project more ambitious than any cathedral or space station. It would be our first physical monument not to our past but to our future, a declaration etched in orbital mechanics and laser light that we are ready to speak and to listen beyond the cradle of our sun. That first Oort cloud transmission would be a shout into a silent forest, but the true test comes not in sending but in receiving. What if one day our shell of beacons begins picking up a structured signal that is not our own? The ultimate challenge for an interstellar internet is not engineering but translation. We would face a network built by minds we cannot fathom, running on protocols written in a logic alien to our own. This is the frontier of xenolinguistics and xenomathematics, the search for a universal handshake in a cosmos of possible minds. Our entire concept of a network is built on layers of agreed-upon abstraction. From the physical cables and radio waves up to the application that displays a video, each layer has a protocol, a set of rules for how to interpret the screaming chaos of electrons or photons into meaningful order. An alien system would have its own stack, its own layered assumptions. The first and most critical task would be to find the bottom layer, the most fundamental bridge between their physics and ours. We would not start by looking for meaning but for pattern. Our computers speak in binary, a language of two states, on or off, 1 or 0, but that is a human choice born from electrical switches. An alien system might use ternary logic with 3 states or something based on quantum spin with a spectrum of possibilities. The raw signal itself might not be a simple series of pulses, but a complex modulation of a laser's polarization or a rhythmic gravity wave. Recognizing it as artificial at all would require filtering out the natural noise of the universe and finding a signature of deliberate design, a signal too orderly, too compressed, or too statistically unlikely to be a pulsar or a quasar. Once we identify a carrier, the real decryption begins. We would need a Rosetta Stone written not in language but in universal truth. This is where mathematics and physics become our first dictionary. The most promising handshake protocol would likely be a broadcast of fundamental constants. Think of it as the alien version of a router sending out a beacon packet. They might transmit the ratio of a circle's circumference to its diameter, pi, as a never-ending string of digits, or the fine structure constant which governs the strength of electromagnetic interactions. These numbers are cosmic signatures independent of culture or biology. A sequence of prime numbers 2, 3, 5, 7, 11 has been a staple of science fiction for a reason. It is a pattern that cannot occur naturally in a simple radio emission. It is a billboard that screams intelligence here. Receiving such a signal would be the first bite of the handshake, a way for their system to say, "We are ready to negotiate a connection." But a handshake is only the beginning. After establishing a basic hello, we would need to bootstrap an entire communication protocol. They might follow this initial beacon with a transmission that establishes their data structures. One proposed method is to send a bitmap image, a grid of pixels where a 1 represents black and a 0 represents white. Starting with a simple 1x2 grid, then 2x2, then 3x3, they could visually teach us how they format two-dimensional arrays. From there, they could send an image of their star system, labeling their sun and planets with binary numbers indicating orbital distance or mass. This builds a shared vocabulary of astronomy. Next might come a periodic table of elements using the universal language of atomic numbers and weights. Each transmission would be a lesson, building up from simple mathematics to complex concepts, all without a single shared word. It would be a painfully slow, meticulous process of reverse engineering their entire framework for representing information, their alien equivalent of our 1s and 0s, our packets and headers. This process assumes benevolence, or at least a desire to be understood. The alien protocol might not be designed for newcomers. It could be an internal system, optimized for speed between its own nodes, with no error correction for outside listeners. Its data packets might be encrypted by default, not for secrecy, but as a standard compression algorithm that looks like random noise to us. Or worse, their entire concept of information might be non-linear, based on quantum correlations or higher dimensional constructs that our linear, time-bound brain simply cannot pass. We might be like a person from the 18th century finding a fiber optic cable, able to see that it is manufactured, but utterly incapable of understanding the concept of modulated light carrying millions of simultaneous conversations. The signal could be right in front of us, a constant chatter of the galactic internet, and we might hear only a hum. The dream of connecting presupposes a shared reality, a common ground in logic and physics. But what if their logic is different? What if their mathematics treats infinity as a common number, or their physics has reconciled quantum mechanics and gravity in a way that renders our constants merely approximate? Their protocol might include instructions or data types that are, for us, logically paradoxical or physically impossible to represent. Decoding their network might not just teach us about them, it could force us to rewrite our own understanding of the universe, one painful, glorious packet at a time. The ultimate firewall may not be one of encryption, but of comprehension. To join the galactic conversation, we may first have to learn to think in a way that is, quite literally, alien. Decoding an alien protocol could reshape our very conception of reality. But if we succeed, the cultural consequences would be even more profound. An interstellar network would do more than transmit data. It would weave the isolated threads of countless worlds into a single, shimmering tapestry. The result could be the birth of a unified galactic consciousness, a shared mind spanning the light years. This is not about conquest or empire, but about the slow, patient merging of perspectives until the universe itself feels like a shared home. For the first time in cosmic history, the lonely fire of intelligence on one world would see the glow of other fires, not as distant, silent points of light, but as voices in a conversation. The crushing existential isolation that has haunted humanity since we first looked up at the stars, the fear that we are utterly alone in the silent dark, would evaporate. We would know with absolute certainty that we are part of a community. That knowledge alone would be the most profound psychological shift in our species' history. Yet with this gift comes a deep and complex dilemma. What happens to the unique song of a civilization when it joins a galactic choir? The network would become a river of culture, carrying art, philosophy, music, and stories from a million different suns. A child on a world-orbiting Tau SETI might grow up with Earth's classical symphonies, the fractal poetry of a silicon-based life form, and the gravity ballet of a species that communicates through complex orbital dances. Their sense of beauty, of meaning, of what it means to be a person, would be a hybrid, a fusion of influences from across the galaxy. New art forms unimaginable to any single world would emerge from this cross-pollination. A musical composition might not be heard, but felt as a pattern of thermal changes and magnetic pulses, designed by a collaborative mind comprising artists from 3 different star systems. This fusion could create a cultural richness beyond our wildest dreams, a renaissance on a galactic scale. But there is a shadow to this brilliance, the risk of homogenization. On Earth, globalization has often led to the erosion of unique local cultures, replaced by a dominant, commercialized monoculture. On an interstellar scale, the same forces could be amplified. Suppose one civilization, perhaps the first to build the network or the most prolific in content creation, becomes culturally dominant. Its narratives, its aesthetic preferences, its social models could become the default standard, flowing down the data pipelines to every newly connected world. Younger civilizations might be overwhelmed, their own nascent art and traditions seen as primitive or quaint compared to the dazzling galactic mainstream. They might choose to abandon their uniqueness to fit in, to be part of the grand conversation. The terrifying possibility is a galaxy where every world listens to the same music, values the same ideals, and tells the same stories, a cosmic empire of the mind achieved not by force, but by the seductive, gentle pressure of shared connection. The network's greatest challenge, therefore, would be to foster exchange without enforcing conformity. Its protocols might need to be designed not just for efficiency, but for cultural equity. There could be algorithms that actively promote and preserve the artifacts of minority or emerging cultures, ensuring they get prominent placement in the galactic library. Quotas for data transmission might reserve bandwidth for indigenous planetary broadcasts, not just the blockbuster content from advanced core worlds. The network itself would have to become a curator of diversity, a guardian against its own tendency to create a universal echo chamber. Beyond art and entertainment, the network would forge something even more fundamental, a truly universal history. Today, our history is planetary, a story of one world. With an interstellar internet, history becomes galactic. The rise and fall of civilizations would be recorded not in isolated stone tablets or corrupted digital archives, but in the immutable, distributed ledger of the network itself. The discovery of a new physics by a species in the Orion Arm would be time-stamped and woven into the shared timeline. The tragic loss of a world to a gamma-ray burst would be mourned across light years, its final transmissions preserved as a sacred digital memorial. This collective memory would create a sense of shared destiny and shared fragility. We would no longer be a collection of solitary experiments, but a single, interconnected story unfolding across the stars. Our identity would expand. You would no longer be just a citizen of Earth or of the solar commonwealth. You would be a citizen of the network, a participant in a project whose scale and duration dwarf all human endeavors. Your daily life, your work, your creativity would contribute to a legacy meant for audiences 10,000 generations in the future and on planets you will never see. This cosmic identity could inspire a new era of responsibility, a long-term thinking that stretches across millennia, because your actions would now be part of a story told to the galaxy. Yet, in the quiet moments, a new kind of loneliness might emerge. The awareness of being one tiny node in an immense, ancient web could feel isolating in its own way. When the conversation spans centuries and includes minds utterly alien to your own, where do you, as an individual, truly belong? The network might connect us, but it could also remind us of our profound smallness. The ultimate cultural impact of an interstellar internet, then, is a paradox. It promises to end our cosmic loneliness by connecting us to others, while simultaneously challenging us to hold onto our unique selves in an ocean of otherness. It offers a shared home, but asks if we are willing to remodel our house to fit the galactic neighborhood. The choice it presents is not about technology, but about soul. Will we use this web to broadcast only our triumphs, or will we have the courage to share our confusion, our poetry, and our quiet planetary sunsets, adding our unique, fragile note to the greatest symphony the universe has ever known? The silence of the cosmos is not just empty, it is a question screaming at us. Enrico Fermi's famous paradox, born from a lunchtime conversation, asks a simple, devastating thing. Given the age and size of the galaxy, why do we see no signs, no ships, no engineering? But our exploration of an interstellar internet suggests we may be asking the wrong question. We have been listening for a shout in a language we expect. What if everyone is whispering on a channel we have not yet learned to hear? Perhaps advanced civilizations do not send ships as their first emissaries. They send data, the most efficient, the most elegant, and the safest way to explore and influence the galaxy is not to move mass, but to move information. A single self-replicating probe could weave a communication web across the entire Milky Way without ever carrying a single biological passenger. The great silence, then, might not be an absence of life. It might be the quiet hum of a network operating on principles we are just beginning to grasp. Consider the possibility that their network traffic is simply too efficient for us to notice. Our own radio and television broadcasts bleed into space as a chaotic, wasteful spray of energy, a bright but messy signature of a young civilization. A mature interstellar network would not waste a single photon. It would use tightly focused laser links, or perhaps something like neutrino beams, where the signal is so concentrated and penetrative that almost no energy scatters into the void for us to accidentally intercept. It would be like trying to detect a conversation by listening for the sound of a pen writing on paper from a mile away, while that conversation is actually happening over a perfectly insulated fiber optic cable buried deep underground. We are listening for the scratch of the pen and hearing nothing while the entire library of Alexandria is flowing silently past us. Then there is the layer of encryption. On our own internet, sensitive data is encrypted, turning meaningful messages into what looks like random noise. A galactic internet would almost certainly employ encryption as a standard, not just for secrecy, but for data integrity and compression. The entire chatter of a civilization, their science, their art, their daily news, might be transmitted as what appears to us to be a perfectly random, natural static. We would filter it out of our search algorithms, dismissing it as the thermal noise of a gas cloud or the faint crackle of the cosmic microwave background. We are searching for a deliberate, repeating pattern of ones and zeros, but their entire culture might be hidden inside a mathematical lock we do not have the key to see, let alone open. But the most mind-bending possibility is that the technology itself is unrecognizable. We assume communication must involve electromagnetic waves, things we can catch with a radio dish or an optical telescope. But what if a mature network uses a medium we cannot yet detect or comprehend? What if they have learned to modulate the quantum foam or send information through microscopic wormholes stabilized by dark energy, or use gravitational waves not as a simple carrier wave but as a complex layered data stream? To our sensors, such a network would be invisible. It would be like an ancient hunter-gatherer standing in the middle of a modern city's Wi-Fi hotspot. The air is buzzing with information, conversations, movies, and financial transactions, but to them, the air is just air. They lack the receiver, the decoder, and even the fundamental concept of what a radio wave is. We could be surrounded by a galactic internet, swimming in a sea of data, and be utterly, profoundly unaware. This reframes the Fermi paradox from a question of presence to a question of perception. The problem is not that they are not here. The problem is that we are not plugged in. We are like a solitary island tribe, listening for the beat of war drums from across the sea, while the continents are silently linked by satellite phones and the internet. We are listening for the wrong signal with the wrong tools at the wrong time. The great filter, the hypothetical barrier that prevents life from becoming widespread, might not be a cataclysm. It might be a transition, the moment a civilization stops broadcasting its noisy infancy to the cosmos and plugs into the quiet, efficient, and encrypted galactic web, disappearing from the cacophony we are trained to search. They have not vanished, they have simply logged on. The quiet hum of a galactic network forces a confrontation with time itself on a scale that shatters all human ambition. We are not talking about a project for a decade or a century or even a single millennium. The full realization of an interstellar internet would be a multi-millennial endeavor, a construction project measured not in years but in geological epochs. To grasp this, abandon every timeline you know. Think instead of the great cathedrals of Europe like Notre Dame or Cologne Cathedral, which took centuries to complete, with master architects laying foundations for a glory they would never see finished. Now multiply that duration by 100. We are contemplating a cathedral of light and data that would take 10,000 years to weave across the local stellar neighborhood, and 100,000 to span significant portions of the galaxy. This is not engineering, it is archaeology in reverse, where we lay the first stone for archaeologists who will not be born for 500 generations. Such a project demands a civilization of a kind we have never been. It requires a society with a stability and a continuity that borders on the mythical. Our human history is a story of rise and fall, of golden ages and dark ages, of knowledge lost and rediscovered. We struggle to maintain infrastructure for a century, let alone plan for 10. An interstellar internet could not survive such turbulence. It would need builders who think in dynasties of civilizations, not dynasties of kings. It presupposes a world or a consortium of worlds that has solved its immediate existential crises, has achieved a lasting peace, and has cultivated a cultural obsession with the long now. The political will to fund a project whose first major milestone might not arrive for 1,000 years is almost inconceivable. It would mean taxing generations for benefits they will never witness, asking them to sacrifice present comfort for a whisper of data that might return to their descendants when the very stars have visibly shifted in the night sky. This transforms the act of construction into an act of faith, the ultimate gift to the future. Every laser array we position in the Oort cloud, every self-replicating probe we launch with meticulous, fail-safe instructions, every line of protocol code we write for deep time, is a message in a bottle with a delivery date set for the year 12,000 or 50,000. We are not building for us, we are building for beings who may be as different from us as we are from the builders of Göbekli Tepe. We would be encoding our values, our curiosity, and our hope into a system meant to outlast languages, nations, and perhaps even our current form as a species. The network becomes a time capsule, but one that is actively maintained, a growing library where each generation adds a new volume to a shelf that stretches into the deep future. What kind of society undertakes such a task? It would be one that has fundamentally conquered short-term thinking. Its economics would have to account for centuries-long return on investment. Its education systems would instill a sense of being a steward in a chain of responsibility that stretches far beyond a single lifespan. There would be custodians, perhaps an entire guild or an artificial intelligence of solemn purpose, whose sole duty is to tend the network, to ensure the Oort cloud beacons remain aligned, to update encryption against future decryption, and to patiently listen for a reply that may not come until after their own civilization has transformed beyond recognition. This long-termism is the rarest resource in the universe, far more scarce than any energy source or exotic material. It is the unwavering commitment to a story whose climax you will never read. And that is the haunting, beautiful core of this entire dream. In attempting to reach out to others across space, we are forced to reach forward to our own future across time. The interstellar internet, if it is ever built, will stand as the greatest monument to human patience, a testament that we looked upon the silent stars and decided to begin a conversation we knew we would never finish. It asks if we can care for something that will only truly serve those who have forgotten our names, if we can plant an acorn knowing we will never sit in the shade of the oak. In that act, we will be answering the deepest question of the Fermi paradox, not with a signal, but with a legacy, proving that a civilization can be measured not by the noise it makes, but by the bridges it builds for those who will come long after the builders are dust. The final challenge is not in the stars, but within us. This journey began with a starship captain's instant message, a fiction that highlights our profound reality of silence and delay. We have traveled from that dream through 6 revolutionary concepts that could one day weave a web between suns. We confronted the unbreakable speed of light, forcing us to invent patient, store, and forward networks that operate on timescales of generations. We explored the leap from shouting with radio to whispering with lasers, and even more exotic ideas like neutrino beams and gravitational waves. We grappled with the staggering vision of self-replicating probe networks building a physical lattice across the galaxy, and the profound security and ethical dilemmas that come with it. We saw how pulsars could become our galactic clocks and how the crushing energy demands might require us to harness the power of stars themselves. Each concept is a response to a universe that does not make connection easy, a universe of vast distance, deep time, and silent, empty space. The obstacles are monumental, perhaps the greatest our species will ever face. They demand energy sources we cannot yet conceive, machines that must outlive civilizations, and a patience woven into the very fabric of our culture. Yet the possibilities are equally breathtaking. Imagine a galaxy where a discovery on a world orbiting a red dwarf star becomes part of humanity's shared knowledge a century later. Think of art and stories flowing between suns, creating a tapestry of experience no single world could ever produce. This network would be more than a tool, it would be a legacy, a gift wrapped in light and sent forward to a future we will never see, connecting us to descendants and other minds across the eons. It redefines our place in the cosmos, transforming a silent, lonely universe into a neighborhood still under construction. That construction begins not with a grand leap, but with the quiet, persistent work happening today. The laser links being tested between Earth and the Moon, the delay-tolerant protocols running on Mars rovers, the steady listening of the deep space network, these are the first stones of the cathedral. Supporting the science of deep space communication, advocating for missions that push these boundaries, is how we lay the foundation. It is a vote for curiosity, for connection, and for a future that reaches beyond our own horizon. So, as we look up at the night sky, consider this: if we could encode a single message, one bundle of data to represent humanity on that first interstellar transmission, what would it contain? Would it be a theorem, a symphony, or the sound of a child's laughter? The answer says everything about who we are and who we hope to become in a galaxy waiting to hear its first hello.